Tracking and predicting projectiles, or catching a ball, is a process taken for granted by humans. However, in the worlds of computer vision and robotics, this problem is deceptively hard. In this video, we will discuss our ball detection and projectile path prediction methods for our final project in the class EECS 498 at the University of Michigan. Ball detection and projectile path estimation can be a difficult problem. However, correctly determining a ball's position and accurately estimating a path is an essential procedure to begin sending a robot to a landing zone, allowing that robot to catch a ball thrown before the projectile's first or subsequent bounces. The difficulty arises from the necessity to accurately detect and estimate a projectile's point in 3D space relative to a predefined origin. Due to the nature of camera vision speed, there's a lot of noise in image processing, and this leads to potentially false detections and inaccurate data sets. If a few points corrupt our detected dataset, then the possibility of sending a faulty path for our bot has a high probability. Additionally, because correctly estimating a bounce path requires constant path updating and bounce factor estimation, dealing with latency becomes an essential factor of real-time projecting computing. In order to account for these problems, we implemented subsystems that provide robustness to our overall project. Those items include image processing, blob detection, filtering, and categorization, linear regression, and bounce path approximation. Using all these subsystems to detect and correct a ball's trajectory in 3D space, we were able to actively move and align a robot to align itself with the landing position of a projectile in real time.
To track the ball's location throughout 3D space, we used a Microsoft Kinect. The Kinect has two cameras. One displays RGB video using a Bayer pattern. The other is an infrared camera used to estimate the depth of objects in the environment. To track the locations of balls, some methods ended up working better than others. First, we tried to use HSV filtering to isolate the location of the ball. We initially thought this solution would be fine, but problems quickly arose. For instance, if anything in the background had a similar hue to the ball we were using, our algorithms could have trouble isolating the ball. We also realized that because of the parallax between the RGB camera and the depth camera, the pixels in each image did not have a one-to-one correspondence. This meant finding the depth at a certain pixel in the RGB image was difficult and unpredictable. These problems encouraged us to try to rely only on the depth image to extract the location of the ball. We found the best way to do this was to implement background subtraction. Our background subtraction algorithm takes the depth at each pixel of the image and averages it over a certain number of frames. Any new frame is compared to the accumulated average, and depths within a certain threshold are subtracted. This method causes anything moving in the frame to stand out. Like HSV filtering, background subtraction is also subject to noise. The depth at the edges of objects tend to jump between background and foreground values. This causes them to never get subtracted. To work around this, we use Union Find to group blobs of foreground pixels together and ignore blobs below a certain size. Once we have a blob of depth values that represents the ball, we get its x-coordinate by averaging out all the depths to approximate how far away that ball is from the Kinect. We then use ray projection to obtain the real-world y and z coordinates from the x and y pixels of the image. Once we have a complete 3D coordinate, we send it over LCM to another computer running our projectile tracking software.
Our prediction for the landing position of the ball assumes that the ball is in projectile motion when the Kinect sees it. In projectile motion, we assume that gravity is the only force being applied to the ball during its flight. Due to the low speeds and short time aloft, we ignore air and ground friction. For a given ball trajectory, there are 6 unknown parameters that we need to estimate. These unknown parameters are the initial positions and velocities in the x, y, and z directions. We need a minimum of 2 measurements to estimate the initial positions and initial velocities of the ball. Using only 2 ball measurements to predict landings in the future is inaccurate because the measurements are susceptible to noise. To increase the accuracy of the system, we used a least squares regression method to estimate the unknown parameters in a given trajectory. When a new measurement is received by our prediction algorithm, linear regression is performed on the new set of data points to increase our confidence of the 6 unknown trajectory parameters. The different colored dashed lines represent different calculated trajectories based on a varying number of ball measurements. For demonstration of our ball detection and projectile path prediction algorithm, We created a tennis ball catching robot by fixing an open cardboard box to a miniature robotic vehicle. We demonstrated this system in Tishman Hall at the University of Michigan. Although our system did not do a perfect job of catching the thrown tennis ball, we demonstrated that real-time ball detection and path prediction is possible and effective.